Hello everyone, this is video 5.3. We're going to be looking at multiplication involving positive and negative numbers. Up to this point, we've only been really looking at positive numbers, so now we're going to generalize this out to include the full set of integers, including the negative numbers. So let's get started. So let's look at a problem like 5 times negative 2. And we've already talked about this idea that if we have m times n equals p, and that n may not look entirely like an n. Let me fix that. So m times n equals p. That means that we have m groups or m sets, whichever language you want to use, and that there's n in each group. And so then this means that I'm going to have p total units, as my product. So for a problem like 5 times negative 2, I know that I have 5 groups, and I have negative 2 units in each group. And so I can model this using my 2 color chips. If I want to go back to those, 3, 4, 5. And I can see that I have 1, 2, 3, 4, 5 sets of those. And so I can think of this as multiplication by repeated addition. I can add together all of these sets of negative 2, and in the end, I'm going to get 10 negatives or negative 10. So I have 10 negative units at the end of this. That makes sense, easy enough. Now, if I were to switch this around to say negative 2 times 5, now I have negative 2 groups, each containing 5 positive chips. And that's where we run into trouble, because the number of groups is sort of inherently like a distance, and so it's inherently like a positive number. I can think of a group containing positive and negative elements, like we've done here, like we've done in this example, and that sort of makes sense. We can kind of understand what that means if that group contains a negative object, because we've already looked at positive and negative with 2 color chips and we did addition. But what we mean by negative 2 groups kind of doesn't work. So we can introduce this idea and introduce the idea that for 5 times negative 2, I'm going to get a negative product. And so we can understand how a product can be negative. But the commutativity of this problem creates a little bit of an issue. That I can understand what it works like in one direction, but maybe not quite so much in the other direction. So this is our issue. How do we get to where we can look at a problem like negative 2 times 5, or even negative 2 times negative 5, and have it make some degree of sense in something other than memorizing a negative times a negative is a positive, or that same sign makes positive, different sign makes negative, or just by memorization, by learning math sort of by fiat. So one thing we can do is we can introduce sort of definitions and properties. And so one definition that we certainly can introduce is that negative a is a times negative 1. That this is what we mean by a negative. And so once we have that definition, we can start to do some things using commutativity and associativity, like negative a times b is now negative 1 times a times b, and this is by the definition of a negative. This is just how we've defined a negative number here. So now once we have that, we can put this negative 1 on the outside and put a times b on the inside, and this is just associativity. And so now we see that negative a times negative b is just going to be the negative of this product. And so we could even go one step further and say that this is the negative of a times b. And again, this is really just our definition of a negative. That negative 1 times something is the same as negative something. That's really what this kind of definition up here is telling us. So we can work through it this way. I mean, it's a really rigorous definition. I mean, we can see how this makes sense. I don't know how much this is going to resonate with, the average K6 student. I don't know how much is going to resonate with the average K6 teacher, to be totally honest. But it's airtight. I mean, we see how this works. And then we can extend this even further to the case of negative A times negative B, and show that this is negative 1 times A times negative 1 times B. And we could, I know I've switched this around a little bit. We can make this negative 1 times A. We know that this is commutative, so we could put the negative 1 on the left or the right. It doesn't really make a difference. But to be consistent with what we have here, we could probably focus on this definition. Anyway, so now we've got negative 1 times negative 1 times A times B. And so I'm using commutativity here to switch that A and that negative 1 around. And so I've moved those around. And now negative 1 times negative 1 we know is just positive 1. And so this is, we could just say, definition of this product that we know a negative 1 times negative 1 equals a positive 1. Now, this is a logical sticking point because we're kind of using something to prove itself. So this is an issue, how we know this. So we need to define this at some point, that this negative 1 times negative 1 makes positive 1, so we could use it for here. So you can already see we're running into a logical loop here to get that negative times a negative equals that positive. So we need something to kind of help define this before we get too far into the rigor of it, because we need this definition. So there's a couple ways we can build this idea other than using these definitions and properties. So another way we can show this is by building a pattern. And so let's start with a pretty basic problem like 2 times 3 equals 6. And I only say basic because we would have done positive integer multiplication by this point. So there may be some recalling that has to be done, but this is not really introducing that much new. So let's do now below that 2 times 2 equals 4, and we'll do 2 times 1 equals 2. And so we can see that if we take m times n equals p, our n is decreasing by 1. So my n is decreasing by 1, and my p is decreasing by 2. I mean, this should make sense. Students should be able to recognize that I have two groups of 3. So 1, 2, 3, 1, 2, 3. Then I have two groups of 2, 1, 2, 1, 2. Then I have two groups of 1. So I'm removing one element from two groups. So I'm removing 2 elements total. So it should make sense that these sets are decreasing by 2, removing one element from 2 groups. So by the time I get to 2 times 0, this makes 0, and this should make sense. Again, my n decreases by 1, my p decreases by 2, and so now this next step is going to be 2 times negative 1 equals negative 2. Now, we've already discussed this one because we would know what this looks like. This is going to be 2 sets containing, here, I'll make it consistent. We've got 2 sets containing a negative, and so I know that this is going to make negative 2. But this pattern also allows us to do this in the commutative form and show that this is also the same as negative 1 times 2 makes negative 2. Realistically, we could also introduce the commutativity once we've sort of established this from the set model, but this pattern is going to be useful for the second part. So it does sort of set the stage for another idea. So it has a lot of portability to it. So now we can see what 2 groups containing a negative looks like, but now we've sort of solved this problem a little bit. I don't know what negative 1 group containing 2 positive chips looks like. So I can establish that using this pattern. Another way of showing this would be with a double-sided number line. And so my m is staying constant at 2. This is my n, and this is my product. 2, 3, 4, 5. And so my n has gone from, well, we start with 3, 2, 1, 0, -1, -2. And we see that these n's are decreasing by -1. And my p's go 6, 4, 2, 0, -2, -4. They are decreasing by 2. So these are going -2 as we step. This is multiplication as repeated addition, so it should make sense. This is moving linearly because we're just removing addends from a large sum. So yeah, the linear aspect of this should follow. Now we can use this in the second part, building patterns. So after we've established that first pattern, now we can do the second pattern. So let's pick up kind of where we left off in the first part with, say, 2 times -2 equals -4. And now instead of decreasing my n, I want to decrease my m. So here's my m, here's my n, and here's my p, my product. So I'm going to decrease n by -1. And let's look at what that does to p. So now this becomes 1 times -2, and that equals -2. And again, we can look at these models. Oh, that's a negative, not a positive. So this first one is 2 groups of -2. And then the second group is 1 group of -1 and a second group of -1. So 2 groups of -1. Now, what's this net effect? You're going to have a lot of students who are going to want to say this is -2. And the reality is, if we go from -4 to -2, we're increasing by 2. Once students kind of get their head sort of wrapped around how this increase and decrease works with positive and negatives, it's going to make this whole conversation a whole lot easier. And you may have to bring out this number line here and show that as we move from -4 to -2, I'm moving to the right. This is increasing. My next step is going to be to 0, which is also an increase of 2, and that's 0 times -2 makes 0. So here my m decreases by 1 again, and my p keeps increasing by 2. And this is just 2 empty sets. Oh, you know what? No, I did this wrong. Let me look at. So this should be 1 set containing -2. I apologize. So this is 0 sets containing -2, which doesn't really get a drawing per se, I suppose. You can just draw an empty circle. So the next step in this pattern is going to be decreasing this m again, now to -1. This n stays constant at -2. Now what happens to p? Well, it's going to increase by 2 again and become +2. So this becomes -1, this is +2, and now we're where we want to be. We can see, using these patterns, that this negative times this negative makes this positive. It's worth going through this with other sets of factors to show that this is not just a property of -2. This is not just this specific case. This is not a rigorous proof, and we saw the rigorous proof earlier when we were sort of introducing this, the -a times -b, and then using commutativity and associativity to sort of move those pieces around. We can define this -1 times -1 makes +1, and just sort of create that as a definition and build from that if we want to be wholly rigorous about it. But like I said, I don't know how much that really resonates with most students or even with most teachers. I think this pattern is not as rigorous, but it's a lot more convincing. That's a whole other conversation, the balance between rigor and convincing. That's a whole other conversation for another time and probably even a different class. But this pattern certainly introduces this idea pretty convincingly that this negative times this negative makes this positive. Again, we can use this number line here. This is my P here, and this is my M here that goes from 2 to 1 to 0, and then we see this moves as M goes negative, N is constant at -2. We can use this double number line as well to show what's going on. The double number line works a lot better than the set model for reasons we've already discussed. I don't know how to draw -1 sets of something. I know how to draw the -2 that goes inside there, but that negative set in there is a little bit harder to show. You'll hear a lot of students, and you'll even hear some teachers go through some sort of like interesting mnemonics about how these sorts of negatives work together. I heard a teacher one time talking about how you could make a movie showing a swimming pool being filled up. And so that filling up is a positive. And so you could also film a swimming pool being emptied, and then that becomes a negative. And now, if you showed that swimming pool being emptied, which is a negative, and you showed it in reverse, which is another negative, then what would the image look like? Well, it would look like the swimming pool being filled up, and so that shows how a negative and a negative makes a positive. It gives me a headache to think about stuff like that. I also had a student one time talk about how it's easy to remember a negative times a negative makes a positive because when bad things happen to bad people, that's a good thing for society or something. I don't know. It was a little too moralistic for me. I think the problem that I have with those sorts of ideas is that it's hard to make the distinction between when those positives or when those negatives work together to make a positive in a multiplicative way versus in an additive way. Because what I don't want students to do is conflate those ideas and now think that -2 plus -3 makes +5 because, well, a negative and a negative make a positive. Um, so I don't want to introduce that sort of confusion. I want students to understand how this works as a multiplicative structure rather than just as an additive structure. Um, or even worse, that just negatives, whenever I see two negatives, they just make a positive. Um, so, I want to introduce this in a way that's specifically multiplicative in nature. So, as a checkpoint problem, I want you to think about this problem. -1 times -2 times -3 times -4 times -5. So what are we going to get for the answer for this? And then specifically, can we tell the sign of the solution just by inspection, just by looking at the problem? Um, I think the product of 5 by 4 by 3 by 2 by 1 isn't quite as interesting as how students are going to think about how these signs sort of work together. Um, so I'd be curious to hear how you think about those negatives working together, what you get for your sign at the end. Um, so yeah, if you have any questions about this problem, by all means, please bring them to class or hit me up during office hours and let me know. All right, thanks.